Newton's experiments with light and color, revolutionizing optics. In the mid-1660s, a young Isaac Newton was already making waves in the academic world. At just 24, he was fascinated by light and color, a topic that had long puzzled scientists and artists alike. One day in 1666, as sunlight streamed through his room, Newton passed it through a glass prism, carefully noting what happened next. To his surprise, instead of a single round beam of light exiting the prism, he saw an oblong band of colors spread out in a rainbow pattern. This was unlike anything seen before. Newton realized this wasn't just an optical illusion or a trick of the glass. Light itself was being split into different colors. No one had imagined that white light could be a composite, made up of colors that could be separated and recombined at will. Until then, many believed colors were somehow produced by the prism itself or by the materials light struck. But Newton had just uncovered a profound truth: colors were intrinsic properties of light. The discovery of the spectrum, Newton's curiosity about this strange rainbow, led him to a groundbreaking experiment. He allowed sunlight to pass through one prism, which split it into colors. Then he passed this multicolored beam through a second prism, but reversed the angle. Amazingly, the colors merged back into pure white light. He named this band of colors a spectrum, a term we still use today. Through this, Newton proved that white light is not a single entity, but a blend of colors. When light passes through a prism, each color bends at a slightly different angle, causing them to spread out into a spectrum. He had uncovered the hidden nature of light, a feat that would forever change optics and set him apart from other thinkers of his time. Challenges with telescopes. Inventing the reflecting telescope. Newton's studies on light led him to realize that color separation, or chromatic aberration, also affected telescopes. The telescopes of his day used lenses to focus light, but the light would split into colors as it passed through the lenses, creating blurry and distorted images. Newton recognized that this was a fundamental problem with refracting telescopes. They couldn't focus colors uniformly. So, he came up with a radical idea. What if he used mirrors instead of lenses? Mirrors don't split light into colors as lenses do. This idea led him to invent the first functional reflecting telescope in 1668. Small but revolutionary, this telescope used a curved mirror to focus light, about 6 inches long. It gave a clear, sharp image that fascinated scientists of the day. In 1671, when the Royal Society invited Newton to demonstrate his telescope, it was an instant success, and his reputation as a scientist grew. Newton's theory of color. To fully explain his discoveries, Newton developed a theory. Color was not a product of materials or objects, but an intrinsic part of light itself. He demonstrated this by isolating a single color from the spectrum and showing that, no matter how it was reflected, scattered, or transmitted, the color did not change. The objects around us appear to be colored because they interact with pre-existing colored light, absorbing some colors and reflecting others. This theory, now known as Newton's theory of color, overturned the long-standing belief that colors were properties of objects, or that they were created by light's interaction with different materials. Newton had found that colors are already present in light itself, a discovery that rewrote the rules of optics. Clashes with Robert Hooke. As Newton's theories gained attention, he was met with both praise and criticism. Robert Hooke, a prominent scientist and member of the Royal Society, challenged some of Newton's findings. Hooke believed light was a wave, which contrasted with Newton's particle-like theory. Their disagreements turned personal and intense, leading Newton to withdraw from any public debates for years. However, Hooke's challenge pushed Newton further. In a rare exchange of letters in 1679–80, Hooke's ideas spurred Newton to work on gravity and planetary motion. Newton eventually proved that planetary orbits could be explained by a force that acted inversely with the square of the distance, an idea that would contribute to his theory of gravity. Despite their brief collaboration, Newton and Hooke never fully reconciled, and Newton famously withheld some of his greatest works until after Hooke's death. The optics and light corpuscles. In 1704, Newton finally published his full study of light in his groundbreaking book, Optics. Here, he elaborated on his theory that light was made up of tiny particles, or corpuscles. He believed these corpuscles moved in straight lines and could be refracted or reflected, but he also considered that light might have wave-like properties when interacting with thin films, a phenomenon known as thin film interference. Although later scientists would favor wave theories of light, Newton's particle theory laid foundational ideas that would later evolve into the modern concept of wave-particle duality. Mysticism and alchemy, Newton's hidden pursuit. What few knew at the time was that Newton's work in optics was heavily influenced by his fascination with alchemy. He spent countless hours studying mystical alchemical texts, exploring the possibility of transforming one form of matter into another. This wasn't just a fringe interest for him. It shaped his approach to science, leading him to ponder whether light and matter could be converted into one another, a question that foreshadowed discoveries in atomic and quantum physics centuries later. As economist John Maynard Keynes would famously write after discovering Newton's alchemical manuscripts, Newton was not the first of the age of reason. He was the last of the magicians. For Newton, the worlds of science and mysticism were deeply intertwined. His studies in alchemy influenced his thinking about force, attraction, and the hidden connections between objects, which would later surface in his work on gravity. A legacy transformed by new theories, Newton's optical theories shaped the field, but by the early 19th century, scientists like Thomas Young and Augustin Jean Fresnel demonstrated that light behaves like a wave. They showed that color results from the wavelength of light rather than particles of light, as Newton had proposed. The concept of light waves helped explain the interference and diffraction patterns that Newton's theory couldn't fully address. Goethe, the famous German poet, also criticized Newton's approach, especially the idea that refraction could never be separated from color. Newton had concluded that refracting telescopes could never be free from chromatic aberration, but John Dollond's later invention of achromatic lenses showed that such telescopes could indeed avoid color distortion. The influence of optics on modern science. In his book, Newton introduced the use of multiple prisms to spread or focus light, a technique that would be used almost 3 centuries later in the development of lasers. His ideas about optics and color theory created a foundation for centuries of scientific advancement, pushing science from ancient concepts of light toward modern theories of quantum mechanics and wave-particle duality. Newton's Optics was more than a book on light. It was a window into his unique blend of scientific brilliance and mystical curiosity. Today, his discoveries in optics remain a cornerstone of physics, a testament to his relentless curiosity, and a lasting example of how science and mystery once walked hand in hand.